This is a lecture from Open Tuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
Right, well, I hope you've looked at the previous lectures on measures of average and dispersion, because now we're going to look at the normal distribution, which is where I can really explain the importance to us of the arithmetic mean and the standard deviation. Before I do, as a lead-in to hopefully make sense of normal distribution rather than purely learn rules, let me look again at the histogram. We've mentioned histogram twice, I think, once in an earlier chapter, once in the last chapter. But let's check again. Look at example 1 in this chapter. It says the following table shows the annual salaries earned by 150 workers. 0 to 1,000. There were 25. 1,000 to 2,000. There were 35. 2,000 to 3,000. There were 40. And the range 3,000 to 5,000. There were 50. And so for some reason we decided to split them into those ranges, and do note, it'll be relevant in a minute, the first three were ranges of 1,000, 0 to 1,000, 1,000, 2,000, 3,000, 3,000. The last range, we decided to lose a bit of accuracy, we took 3,000 to 5,000, fine. If I asked you to draw a histogram, then if you remember, we had these bars, so where was it? It was 0, 1,000, 2,000, 3,000, 4,000, 5,000. And so we start off just like we did before and say, all right, from 0 to 1,000 there were 25, so I'll draw a bar 25 units high. 1,000 to 2,000, 35. So that's about there. Again, I'm not trying to be perfectly accurate. You wouldn't be asked to actually draw one in the exam. 2,000 to 3,000, there were 40. And then we had about 3,000 to 5,000, 50. Now, it's very tempting to say, oh, let's draw a bar 50 units high. But that is actually very, very misleading. The reason being that we've got a range there that's twice as big as the other ranges. The others were just 1,000 each time. This is 2,000. And so I'm not at all surprised. There's a lot more people in the range 3,000 to 5,000 than there were in the range 2,000 to 3,000. It'd be very misleading to draw that dotted bar as I have. It makes it look as though, ooh, by far most people are earning an awful lot of money. And so what is so important, and important for what follows, is that in fact when we're drawing a histogram, it's not the height of the bars that's proportional to the frequency. It's the area of the bars is proportional to the frequency. Now the area is the height times the width. And so there we are, the first three, they were all 1,000. And so the more people, the higher the bar, no problem. But we now come to a range, I said we've lost some accuracy, fine, but a range which is twice as big, that's twice as wide as the other bars. And so, because it's area, height times width, that's proportional to the frequency, if the range within that, if that range is twice as big, we make the bar half the height. And so that last bar, instead of showing a height of 50, which you would have done if the range was only 1,000, but because it's twice as big a range, we use half the height. And that should make sense. I keep saying we've lost accuracy, but it's like saying, oh, 3 to 4,000 is half of it and 4 to 5,000 is the other half. So they're both 25, and it's now much more representative of what's actually happening. But again, importantly, the area of the bars is proportional to frequency. Now, having drawn that, a couple of things. First of all, let's just look at B and C in example 1. It says, what's the probability of a worker earning between 1,000 and 2,000? What's the probability? What's the chance? Well, we can see that straight from the table. Out of 150 people, 35 of them earn between 1 and 2,000, and therefore, if I were to pick any person at random, what's the chance, what's the probability of them earning within that range? It's 35 out of 150, or, as a decimal, 0.23. Again, I'm keeping to the decimal places. But 0.23 of these people earn between 1,000 and 2,000, or if you prefer, 0.23 is 23%. But that's the percent of people in our sample who earn in that range, and therefore, picking one person at random, the chance they're in that range is 23%, or strictly probability, 0.23. And similarly, what about C? What's the probability of a worker earning more than 2,000? There are 150 workers in total. How many earn more than 2,000? Well, 2 to 3,000 is 40. 3 to 5,000 is 50. So there are 90 in total earning more than 2,000. Well, if 90 out of 150 earn more than 2,000, if I'm to pick one of them, the chance or the probability of them earning more than 2,000, 90 out of 150, which is what? 0.6, or if you prefer, 60%. 60% of our workers earn in that range, and then there's a 60% chance if I pick one of those workers that they're earning in that range. So, I hope that's easy enough. But, to take it one step further, as a lead-in to normal distribution, suppose I didn't give you that table. Suppose I just gave you the histogram and I said that histogram has been drawn accurately. And I didn't give you that scale. Suppose all I gave you was that. I told you it's been drawn properly. You've got the bottom scale 0 to 5,000. And I asked you again, what's the probability or what proportion of workers earn between 1,000 and 2,000? Well, from what I said earlier, the number of people in that range, it's proportional to the area of the bar. The total area of all the bars represents all 150 people. You see, if I've just given you a histogram, you don't know whether there are 1,000 people or 10 people. But I do know the area of all those bars is proportional to the total number of people. I know that the area of this bar is proportional to the number of people earning between 1,000 and 2,000. And so, and don't worry, you're not going to have to do this in the exam, but if I took a ruler and measured this area, and I measured the area of all the bars, then we'd find that this area would be 3550ths, it would be 0.23, of the total area of all the bars. The area of each bar is proportional to the number of people. The area of all the bars is proportional to the total number of people. If that area is 0.23 of the total area, then fine, 0.23 or 23% of the people earn in that range. Or again, C. Again, if I hadn't given you the original table, all I'd given you was that histogram, but told you it had been drawn properly. And I said, what's the probability of earning more than 2,000? Well, again, the area of those bars is proportional to the number of people. The area of all the bars is proportional to all the people. We'd simply have to work out this red area as a fraction of the total area of all the bars. And if we did, and if it had been drawn properly, we would find that those two red bars in total were 0.6 or 60% of the area of all the bars. Now then, as I've said, you won't actually be asked to do that. So you won't be drawing a histogram and you won't be measuring the areas. But the reason that's so important is that would apply to any histogram. And in fact, if you looked in more and more detail, what I mean is, if we had a distribution where the ranges got smaller and smaller and smaller, and so the bars got smaller and smaller and smaller, you would end up effectively with a curve. Instead of bar, 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 some sort of curve. And all this is effectively a smoothed out histogram. And I don't know, it could again be wages, so anything from 0 to 5,000. 1, 2, 3, 4. Now, as I say, all that is a smoothed out histogram. If the bars got narrower and narrower, end up something like that. Well, the same rule would still apply. That if I said, what proportion earn between 2,000 and 3,000, well, the area of those bars, or the area under that, or that shaded area, would be proportional to the total number of people between 2,000 and 3,000. The area of all the bars, or the total area under that curve, would be proportional to all the people. And so if, making up a figure, if that shaded area was, let's say, 40% or 0.4 of the total area, then we could say 0.4 or 40% of the people earn between 2,000 and 3,000. Or there's a probability of picking somebody of 0.4 who earns between 2,000 and 3,000. Now again, you won't be drawing a curve of frequency distribution. You won't be measuring the areas. I don't know if any of you did it at school, but I remember using graph paper and saying 1, 2, 3, 3.5, 4, counting squares on the graph paper. You won't be doing that. But for one particular shape of curve, there are tables which tell us what those areas are without us having to measure. And it's called the normal distribution. Now, in fact, the normal distribution, this curve, a normal distribution is a very precise shape. There's a very precise equation. But essentially, any curve which has what I'm about to list as what you might call the attributes is near enough for what we need. A normal distribution looks like this. Yes, I've drawn that reasonably well. It's where, you see, the frequency distribution, as I just showed you, could end up being any shape. We call it a normal distribution if it's symmetrical about the mean. And what we mean by that, the mean is in the middle. And symmetrical, it's the same on both sides. So it's like a mirror image. The same on both sides, goes up, goes down, about the mean. It's continuous. So there's no sudden jumps anywhere. It's a nice smooth curve. The mean and the mode are the same. Now, I've explained what they both mean. The mean is the average, and if it's symmetrical, that's right in the middle. And also, the mode is the most popular observation. Well, it's the peak, the top, the most popular. We say it's bell-shaped. I hardly need to explain that. It looks like a bell. And strictly, although I haven't listed, and I'm less worried, it's what we call asymptotic. What it means is it gets closer and closer to the axis at both ends, but in theory never quite touches them. Now, in real life, it'd be a miracle if a distribution was what we call perfectly normal. But any distribution which is more or less that shape, we say is near enough for us to do what we're about to do. And we're going to use the same principle as I did before. That, you know, if this were wages and it was 0 to 5,000, this is only a smoothed out histogram. And so we can get any proportions we want by looking at the area under the curve. Now let me explain exactly what I mean with example 2. A company produces units with an average length of 10 centimetres, so the arithmetic mean is 10 centimetres. The standard deviation, or sigma, is 0.2 centimetres. Now we know how those were calculated, and although you could have been asked to calculate them in other questions, in these questions they'll be given. And it says what proportion of the units will have a length of more than 10 centimetres, between 10 and 10.4, and so on. Well, we assume that it's normally distributed. It's a bit skew-whiffed, but I have to explain what normal distribution looks like. The average is 10. The mean is 10 centimetres. And part A, I'm sure, if you understood me so far, you could write the answer straight down. It says, what proportion of the units will be longer than 10 centimetres? Well, what do we want? Remember, The area under the curve is proportional to all the units. We want those that are more than 10 centimetres. Well, that area there is proportional to the number that are more than 10 centimetres. So we need to know what proportion is the red area. What proportion is it compared to the total area? Well, remember, it's symmetrical. And so surely, if the mean is 10 centimetres, 50%, 0.5 are higher, 0.5 are lower. So I don't need any further arithmetic. That red area must be 50% or 0.5 of the total area. So we can say 0.5 of our units, 50% of the units, would be more than 10 centimetres long. Now then, although that should make sense straight away, what about the next question? I know the average is 10, and it says, what proportion of our units will be between 10 and 10.4? Suppose 10.4 is there. In this case, that red area is proportional to the total number between 10 and 10.4. The total area under the curve is proportional to all the units. So if that red area was 10% of total area, it would mean 10% of the units were within that range. If that area is 1% of total area, it would mean 1% of the units were in that range. Well, how are we going to do it? The proportion depends on the spread. What I mean is, suppose the curve looked like this, where everything's very close to 10. The proportion between 10 and 10.4 is very big. On the other hand, if the spread is a lot greater, the proportion between 10 and 10.4 is a lot smaller. Well, to get the proportion for a normal distribution, there are tables which you're given, and I'll show you in a minute, which will tell us the proportion. But because it depends on how big a spread there is, when we use the tables, we look up, it will tell us for any distance from the mean. So the distance away from the mean, 10.4 minus 10 is 0.4. However, because that, if there's very little spread, 0.4 is a big difference. If there's a big spread, 0.4 is a tiny difference. We measure the distance from the mean, the average, in numbers of standard deviations. Now we know for this question the standard deviation is 0.2. How far away from the average are we? Well, 10.4 minus 10, I'd already written down. We say, well, how many standard deviations is that? Well, if one standard deviation is 0.2, surely 0.4 divided by 0.2 is 2 standard deviations. And as I'm about to show you, there are tables which will tell us the proportion, that area we're after as a proportion of total area. We can do it for any area as long as we have the distance from the average in numbers of standard deviations. And we call that the z-score. And the z-score is the distance away from the mean, x minus x bar, divided by the standard deviation. So again, although I've already written it down, we're looking at 10.4 as against a mean of 10. Standard deviation of, I've lost it, 0.2. And so the distance is 0.4 away, divide by the deviation, it's 2 standard deviations. Now remember what it is I'm after. I want to know the proportion between 10 and 10.4. I need that red area as a proportion of total area. Well, I'm about to show you, you have tables in the exam which will tell you the proportion for any distance away from the average, the mean, measured in numbers of standard deviations. Here we're talking about a distance 2 standard deviations away. Well, let me show you how the tables work. These are the tables you get given in the exam. And these tables tell you, see, they write it as x minus mu, which is another symbol for x bar, but that doesn't matter. To find the area under the curve between the mean and a point z standard deviations above the mean, use the table below. Well, how many standard deviations away are we? It's 2 away. So we go down the side, no. We need to go further. There, 2. And the reason we've got columns is it gives you a second decimal place. So if you look at the headings for the columns, the first column is 2.00, the second column is 2.01, the third column 2.02, and so on. Well, we want 2.00. So 2.0 down the side, 0.0 along the top. And I hope you found it, 0.4772. And what it means, if I can get back to where we were, there we are. It means that the proportion that are between 10 and 10.4 centimetres, it means that area under the curve is 0.4772 of the total, or the proportion is 0.4772 of 47.72%. Now think about that. Wind back if you need before we do part C. But these tables will give you the proportion for any number of standard deviations away from the mean. Let's look at C. You don't have to draw a picture. I always find a little picture helps me, Clear what's happening. Again, we're assuming we've got a normal distribution. The average, remember, is 10 centimetres. But what do I want this time? I want the proportion less than 9.8. So I need that little bit of shaded area. Now the tables won't give me that directly. The tables will only give me the proportion between the mean and some other point. Now I know, remember, it's symmetrical, so I know that below the mean is 50% or 0.5. I want below 9.8, but if I can work out that area there, the difference between the mean and 9.8, then subtract from 50%, we've got what we want. So again, you can only look at directly between the mean and some other point. And that distance is 0.2 centimetres. The distance we always look up in numbers of standard deviations, the z-score. So z, the difference between the mean and 9.8, divide by standard deviation, which is 0.2. And so the z-score, 0.2 divided by 0.2, is 1.00. That distance there is 1 standard deviation away from the mean. Now, because it's symmetrical, it doesn't matter whether you're 1 deviation above or below the mean. I keep saying it's symmetrical. But now let's use our tables to tell us what the red area is. So, check with me again. It's 1 down the side. And here again, I want 1.00. It's 0.3413. And so, this area there, the red area, is 0.3413 of the total area. That's the proportion between 9.8 and 10. But of course, I want this area here. But as I said earlier, because it's symmetrical, below 10 is 50%, 9.8 to 10 is 34%, and therefore, to be less than 9.8, it must be 50% of 0.5 minus that area there, 0.3413, which is 0.1587, is it? I better check. 0.5 minus 0.3413. Yes, 0.1587. What does it mean? It means 0.1587, or if you prefer, 15.87% of our units are below 9.8 centimetres. Or the chance of picking just one unit, which is less than 9.8 centimetres, is 15.87% or 0.1587 probability. So that's all it is. It needs practice, obviously. But again, at the risk of repeating myself, remember, using the tables, we were able to work out the proportion of any area between the mean and some other point. So we can get between 10 and 10.4, we can get between 10 and 9.8, and so on. But we could need to play around, as I did there, to be less than 9.8 or more than 10.4. You can't look up directly, but because it's symmetrical, below 9.8 is 50% less the proportion of 9.8 to 10. All right, we're virtually there, but for safety, it's possible you could be asked to effectively use the tables backwards. And let me show you what I mean in the last example, example 3. For the same information as in example 2, so example 2, remember, with a normal distribution, the average is 10 centimetres, and the standard deviation is, what was it? 0.2 centimetres. But this time, instead of saying what proportion between 10 and 10.4 or whatever, it's saying there's a 95% or 0.95 probability the length will be more than X centimetres. So here it's sort of giving us the answer. You know, before we knew the distance away and the tables would give us the probability. Here It's saying the length will be more than X centimetres with a 95% probability. Well, we know there's a 50% chance they're more than 10 centimetres. It's symmetrical. And we want there to be a 95% chance, so surely it must be less than 10. I want to know what is X, so that the area, the proportion, is 95% or 0.95. Because if that shaded area is 0.95 of the total area, then there's a 95% probability that the length is more than X. Well, we're going to have to work backwards. Remember, the tables will give us the proportion between the mean and some other point. So if I knew what this was, if I knew the z-score, we could look up in the tables and it would give us this area. But here I know what I want that area to be. Surely if there's a 95% chance of being more than X, if the chance is 50% of being more than 10, then this area must be 45%, or 0.45. 45 plus 50 is 95. And so whereas before we looked up the z-score and got an answer of 0.45, this time we're going to look backwards and say, well, what's the z-score that gives an answer of 0.45? Look again at the tables. Before we knew the z and we got an answer, 0.34, 0.47. But now I want to know what z gives me an answer of 0.45. Let's have a look. 0.44, 0.4554, that's too big. So 0.44, 63, 74, 84. That's 0.4495, which is, remember how we read it? It's 1.64. 0.4505, it's sort of in the middle of the two. Remember, I want an answer of 0.45. Well, it's between those two, 4595 and 4505. Between 1.64 and 1.65. Now, by all means, just use 1.64, although I'll take halfway between, because it's halfway between those two, I'll say, the z-score, working backwards, is 1.645. So looking backwards, what do we want the answer to be? 0.45. And what z gives us an answer of 0.45, and it's 1.645. The z, remember, is the number of standard deviations. How many centimetres is that? Well, one standard deviation was 0.2. And so 1.645 times 0.2 is 0.329. Now, we're not quite there, but we're saying that the value we're after, x, is 0.329 centimetres below the mean. And so what is x, therefore? The mean is 10 centimetres. Having used the Z's, it's 0.329 below that. (9.671). And so what's it telling us? We now know that 95% of all units will be more than 9.671 centimetres long. And recapping, how do we know that? We know that that's 9.671. We know that, repeat example 2 on these figures now and check yourself. But we know that the proportion between 9.671 and 10 was 45%. We know that more than 10 is 50%. So we know that in total 95% of all units are longer than 9.671 centimetres. And there we are, that's normal distribution.